This code is a MM1 queuing system was simulated and a graph depicting the relationship between throughput and load was plotted. Here is the simulation during is set to 200 steps. Multiple different laws are used to observe the system performance. And class simulation uh, re, re, represents an instance of a queuing system that caps a load. A store here is store events using the list heap, and here is server busy. Whether the server is processing customers and uh, and here is a, and here is the schedule arrivals. When initializing, arrange the first arrival event first. According to according to the person process, the time of the next arrival event is randomly generated, and the departure and the scheduled departure. According to arrange the departure events for the compilation of the servers, and here is the main function. Uh, Arrange it at each step, retrieve the earliest current event, and update the clock. If the event type is arrival or departure, call the corresponding process function. And handle arrival. The number of arriving customers has increased. Arrange the next arrival event if the server is idle. Arrange the leave immediately, otherwise end the queue. And is handle departure. If the queue is not empty, continue to server severe the next customer in the queue. Otherwise, the server become idle. Uh, through throughout throughput rate equal number of completed servers divide number of arrivals. The average waiting time equal the total waiting time of all waiting customers divide the number of waiting customers. For each load value, create a new simulation and run 200 events. Record the throughput rate each time. When the arrival rate is less than the service rate, the system can handle the arriving customers quickly, and the throughput rate is relatively high. When the arrival rate approaches or exceeds the service rate, the system becomes congested, the waiting queue grows, and the throughput rate decreases. And this is uh, the second code, and it's a simple Python script to how to generate the random number using the exponential distribution. It utilizes the random exploratory methods. It's a standard library used for generating random numbers. Make the random number consistent each time is to run the testing and the debugging. If no seeds are set, the number generated each time will be different. The second, the cancel output test indicating that the data to be printed next the expansion process, and it cycle 10 times. generate a random variable that follows an exponential distribution with a rate lambda equal 10. Format the output as a four-dimensional places. And this is the third code. The MMEQ system was simulated and access lasted on the varying lots for the following throughput, average delay, server utilization. Uh, Here is initialize the system state and parameters called schedule event to schedule the first arrival event. The default survival is rate is 18. Is 18. Here is return. Here is generated a return time that follows an exponential distribution. This is data. This is using a main heap to save the event list or sort it automatically by the time of event occurrence. Pop up the event with the earliest time each time and handle it. Event type arrival equal 1 co-handle arrival, departure equal 2 co-handle departure. If the survivor is running the last survivors and it has not been processed yet, count it to total busy time. Add one to the number of arrivals. Schedule the next arrival. If the serial is idle, so server immediately and schedule departure. Otherwise, queue up. Add one to the number that leaves. If the queue is not empty, the next customer is queuing up. Calculate the rating time. Appointment schedule survivors. If the queue is empty, the server become idle. Record the during of this service. Uh, throughput equal number of departures divide the number of arrivals. Average latency equal total waiting time of all waiting users divide number of waiting users utilization rate equal busy time divided total simulation time. Perform a simulation for each load once and save the results. Throughput approaches 100% when the load is less than the service rate. Average latency increase with the increase of the load congestion. Utilization approaches 100% as the load increases, which may eventually lead to system congestions.
Uh, for the first part, this Python script generates 1,000 pseudo random numbers between 0 and 1 using the built-in random model and plot them as a scatter plot to visualize their distribution. A fixed random seed, 13,579 ensures uh, reproducibility, meaning the same sequence. 嗯，
到哪了，英哥？
不是，我要那个先介绍一下这个代码的作用，然后那个再那个说。那我重新开始吧，然后我会说那个就是 starting with the first line。我到时候会说，我先介绍一下这个代码，好吧？
OK OK，
那个浩哥重新录吗？
没事，等会直接讲就行了，等会剪掉就行。
行，OK。This Python script generates 1,000 pseudo-random numbers between 0 and 1 using the built-in random model and plots them as a scatter plot to visualize them distribution. A fixed random say the 13,579 ensures reproducibility, meaning the same sequence of numbers is generated each time. The index of each number from 0 to 999 is used as the y-axis, and the corresponding random value is used on the x. The result is a vertical scatter plot that illustrates the uniform spread of the random values across the 0 to 1 interval. So we continue with the first line. Import the required models. This For the first imports Python's built-in random model, which contains functions for generating random numbers. The second is the pyplot submodel from the matplotlib library and gives it the Alice plot. This model is used to create plots and visualizations. Then we set a fixed seed to the random numbers. Set the seed for the random number generator to 13,579. This ensures reproducibility, meaning the same sequence of random numbers will be generated every time you run the script. Then the list to store values. We create two empty lists to store. The first is for this both for generated random numbers. Uh, then generate 1,000 random numbers. Loops from I equals 0 to I equal 999, repeating the block 1,000 times. Then generates a random float between 0.0 and 1.0. Then we print the number. We add the current index I to the index list and add the generated random numbers x to the rand value list. Then we plot the random values as a scatter plot. We create a scatter plot. X shows the random values and Y shows the index. Set the title of the plot to empty person random. Then we label the y as contents and label the x to show the range of generated value. Then we display the plot, so we can see the plot on the screen. Okay, next code. Okay. For this code, this Python script implements a custom pseudo-random number generator uses a linear generator LCG algorithm with large constants for the multiplier, increment, and modulus. It uses the current system time as the initial seed and generates specific numbers of normalized normalized random value. We set the default is 1000 and the first few values are printed to the console for inspection, and all generated values are plotted as a scatter plot to visualize their distribution between 0 and 1. This provides a basic demonstration of how LCGS can be used to simulate random number generation. And for the first line, we import Python's built-in time model, which allows access to time-related functions. Used here to obtain a dynamic seed, and we import the pyplot submodel from matplotlib. Seems like last code. And we define a function named runBit with two optional parameters. The first is count equal 1000 and second is showPrint equals 10. Then we give three LCG formula. The A is multiplier, the B is increment, and N is modulus. These values are large integers to enhance the statistical quality of the generator. Then we use current time as seed. Uh, the first seed the first is seed initialization. Time gives the current time in seconds as a float, multiplying by uh, 1e7 shifts it to microseconds. Then we ensures the seed value remains manageable. The result is converted to an integer to serve as the initial seed x. Then we create the empty list. The name is values. Then we give the function repeats count times. Our default is 1000 and we use this function x equal a uh yeah a multiply x and add b. Then we get the result and modulo the n. Then we can get the result. Then we print the first few generated values and print the first show print values. Use the for function. Then we create the plot. The first line is the plot finger. We set the size and range x range is from 0 to count 1 and y values is y axis normalize the LCG generated values. We set s equals 8 and marker size is 8. Then we set the plot titles. We set the label. Title is LCG generated random numbers, and we add the grad. Uh, Enable grad lines. Then we display the label LCG values from the scatter plot. Then we um, can read the plot window on screen. Next code. For this code, this Python code defines and uses a linear congruent congruential generator to generate a sequence of pseudo-random numbers. The function LCG takes parameters for the multiplier, increments, modulus, and initial seed and generate a specified number of values. Each number is computed using the LCG formula. The generated values are printed with their index. In the example, it generates 99 values using specific parameters and prints them to the console. Then the first line is we also import the library. And the second, we define a function named LCG, and we have six parameters. A is the multiplier, C is the increment, and M is the modulus. C the starting value, and count is the number of random values to generate. Then the verbose is a boolean that determines whether or not to print the generated values. Then we set the x equals seed. It's initialize x with a given seed value. This is the starting value for generating the pseudo-random sequence. And we create an empty list named values to store the generated random numbers. And code loops loops contents to generate from I equals 0 to I equals counter to generate the desired number of pseudo-random numbers using the LCG formula, and appends the new value of x to the list value. If verbose is true, print the current index and the value of x. Uh, then we call the LCG function with the following parameters. We give the example parameters so we can get the result. Next code. This Python script simulates an MM1 queuing system to evaluate how different arrival rates affect system throughput. For each load value from 10 to 200, it creates a simulation object that models packet arrivals and departures using ex- exponential distribution. Events are managed using a priority queue, and the simulation tracks metrics like the number of arrival, uh, departures, and queue waiting times. Each simulation runs for a fixed number of events, 200, and the throughput is calculated and stored. Finally, the script plots the relationship between load and throughput using a line graph. We also use import to have three library. The first is provides a priority queue for managing future simulation events efficiently, and the random is for generating pseudo-random numbers, and matplotlib is used to plot throughput with load after simulation, and we set the parameter. The first is ARIVAL equals 1, and its constants used to identify event types. And the second is simulation time, uh, number of events to simulate per load settings, and throughput. We set a empty list to store the throughput for each load. And the loads is a list of different arrival rates. The lambda to test the service rate mu is fixed at 20. Then we simulation class for MM1 Kun. Class simulation represents one run of a discrete event simulation for an MM1 Kun. The first is initializes the simulation with a given load and two independent random generators. And self clock is the simulation time, and the self event list is a prior- priority claim to star future events, and the load is the arrival rate is the lambda for this simulation. And Queen is we use the FIFO for waiting packets, and the survey busy is we set the survey busy is false, and it's a boolean flag to check survey status, and the arrival rate is the current simulations load. The service rate is fixed at 20 packets per unit time, and the self-arrival range is we custom random number generators to allow repeatability, and for statistical contents, uh, uh, make it down. Okay, the statistic the statistics counters we use NPA and NPD and NPQ. The first is number of packets arrived. The second is the number of packets departed. The third NPQ is number of packets waited, and total wait time is accumulated Queen delay time. And we self-init event list is a initialize first arrival event, and we use this exponential distribution to schedule the first arrival at time, push it into the priority queue. Then we soonest event from the priority queue, updates simulation time and set the event time. Then we handle event based on type. Uh, if self event type equals arrival, we set the self arrival events. We use this function, cause appropriate handle for arrival or departure. And we generate interval is we exponentially distribute interval time based on lambda. Then for service, generated service is exponentially distribute service time based on mu. And the arrival event always schedule the next arrival, even if the server is busy, and if server is idle, server immediately. So otherwise, for the self queen append. Otherwise, queen the arrival time for delay calculation later, and we count this arrival. Uh, self point NPA at equal 1 is increment packet arrival count, and the departure event is increment packet departure count. Then we set the self queen. The first is arrival time and the wait time and total wait time and NPQ. If queen is not empty, remove the next packet from the front. Calculate its waiting time and update total queen statistic. Okay, done. Service time. Schedule the next departure event, and else is if no one is in the queen survey becomes idle, and we depth the results. Calculate throughput as departed multiply 100 and appends to global throughput list and prints the results for the current load. Then we have the plotting function. We have the plots throughput and load using matplotlib. Done. Use dots to highlight points and grid improves readability. And our main simulation loops through all 20 load levels from 10 to 200 and sets fixed seeds for reproducibility of arrival and service time generation. Then we create a new simulation object for this load level and runs the simulation for 200 events and prints and records the result for the current load. Then we plot the throughput against varying load values. Then we can get the results. Okay, next code.
Okay. Okay, this part, the first is parameter for exponent discrimination, and the the first one is the number is every waiting time equals 10 10 meters, and the number of simulated paragens. The x is the max to capture 98% of distribution. X x minimum. The next generate waiting time using exposure distribution. And here is prepared PDF and CDF. The next this part is calculator means and variance, and this part is prepare figure one prepare PDF add histogram. The next part figure two is prepare CDF, and the last is this display. And from the result, the this picture is bus waiting time. The the bus is simulated waiting times. The blue code is theoretical exposure PDF. The red dashed line is mean waiting time at 10 meters. 10 meters, and the observation is simulated to the data closed machine. The exponent code confirm the model's accuracy. This picture is cumulative distribution for bus wait time. The CDF, the CDF pro, the purple line is CDF increased rapidly, approaching 1. Tell you the chance that a person waiting less than X meters. For example, from the point, uh, the P wait less than 20 minutes equals 0.86. Next, this is part is the parameters for bus waiting time. This part is rate bits per meters, and the number of samples. And the figure one is prepare PDF and histogram, and the picture two is prepare CDF, and this part is generator and pointer for each lambda, and this part is generator waiting times using inverse transform. the under the uniforms from 0 is 0 or 1. This part is invest transform sampling, and this part prepare X, PDF, and CDF. The pollen histogram and the PDF from the result. The result is CDF for bus waiting time. Uh, a histogram of generated waiting times from the blue bar from the from the from the when lambda equals when lambda equals 20 left, the bars are less frequent and longer average waiting time, and the histogram is round and flat. When lambda equals 8 rest, the bus the bus arrive very frequently, and most people wait a short time. Histogram is narrow and sharply peak near nearing zero. This this demonstrated that higher lambda, shorter expanded waiting time, and steeper exposure DC. This one when lambda equals 20. It's take a it's take a longer to reach probably equals to 1, and for lambda equals 8, the curve is much faster. You almost certain to catch a bus in under 0.02 minutes. That's the from this code. This part is similar to rolling a far 6 side stack. The code is for reproducibility, and the range you can change this to 10, 100, and this part is print first 10 rows for checking. This part is calculated the probability mass function, the PMF. This part is CDF, calculated the CDF. And this part is calculated descriptive statistic. And this part is print the statistics. And this part is pollet the PMF using steam pollet. This part is pollet the CDF. For the result, the PMF of rolling a failed die. The PMF shows the impartial probability of which outcomes from 1 to 6. all probabilities are one uh, close to 1 or 6. As expected, the steam point confirms that each number has a nearly equal chance. From the CDF of rolling a fair die, the CDF shows the cumulative probability of getting a result less than or equals to certain numbers. From the fair die, the the zero ticker CDF is when x x equals 1 the equals 0.167. The red line in the point increase linearly and reflecting a uniform distribution. Okay, that's all. Thank you.
Okay, thank you, thank you.